Thank you for that kind introduction. I'm Borgentun and I'm with Thorlabs Sweden in the Research and Development Department working with the optical instruments. And today's talk, I'm going to show you some of the spectrometers that we have in the Thorlabs catalog, and especially I'd like to welcome the newest member to that family, the Redstone. Now Thorlabs has two other webinars in the spectroscopy field. Yesterday, Dr. Oswald talked about his large field of view Raman spectroscopy with some nifty coded apertures. And also yesterday, Dr. Fisher showed his multivariate optical elements for real-time chemical sensing. Please visit our website to check those webinars out if you haven't already. But right now, I'll show you some of the spectrometers. I'll briefly review the instruments, and then I'll perform some demo measurements. The first instrument I wanted to talk to you about is the Scanning Fabric Pro interferometer. It's a cavity consisting of two highly reflective mirrors, and the length of this cavity is tightly controlled with piezoelectricity. This makes it easy to resolve really narrow spectral characteristics of your narrowband laser source. Next up, we have the compact CCD spectrometer. It's a small, rugged design with a grating inside which splits up the input light over a CCD sensor. You can make over 200 measurements per second. For instance, if you want to do reflective color measurements, you can use a cosine corrector on the fiber end to do that. Then we have the OSA 20X Optical Spectrum Analyzer. It's based on a Michelson interferometer design and uses Fourier transform to obtain the optical spectrum. It's a general purpose instrument for all kinds of light sources, and even has two input ports, a free space port and a fiber input port. You can use it to characterize your narrowband source or your broadband source, or take a look at the gas absorption lines. And finally, we have the Redstone Optical Spectrum Analyzer. It's the OSA 20X's big brother. It has everything the OSA 20X has, and then some more. And I'll show you all the specifications in the presentation now. The OSA 20X and the Redstone Optical Spectrum Analyzers have a lot in common. They're both based on a Michelson interferometer design. They both have two input ports, the free space input port and the fiber input port. And they both come with a laptop and a software GUI that makes it easy to display your data, and it has a lot of analysis tools. But the Redstone has 4 times the resolution of the OSA 20X. It also has 2 detectors, allowing for a wider wavelength range with the Redstone, and a good sensitivity. And the free space input port of the Redstone is larger, so it collects more light and can detect weaker sources than the OSA 20X. The Redstone has an internal broadband reference source, and with this we can determine the accurate location of the center burst. Thus we can average interferograms, which makes the SNR better. And finally, the Redstone gives the user access to its internal reference laser source through the calibration output on the front panel. This reference laser is a DFB laser frequency locked to an acetylene gas cell, and it emits light around 1532 nanometers. The user can do calibration with this laser or do measurements. As mentioned, the Redstone is based on a Michelson interferometer design, wherein the input light is split up into 2 optical branches with a beam splitter. The 2 branches are then reflected back with retroreflectors to the beam splitter where they recombine. One of the retroreflectors is mounted on a moving platform, thereby creating a difference in the path length between the 2 branches. And this creates an interferometric pattern on the detectors. We can then use Fourier transform to obtain the optical spectrum. The other retroreflector's position can be optimized with piezoelectric transducers so that the overlap between the two branches is optimum. We also have attenuation filters in front of each of the detectors, allowing for higher input power without destroying any of the detectors. The first model of the Redstone will cover the wavelength range of 1000 through 5600 nanometers. Here you have a plot comparing the resolution of the OSA 20X and the Redstone. As you can see, the highest resolution of the Redstone is 4 times better than the OSA 20X, and we have 4 different resolution settings for the Redstone. The specifications are listed here partially. The highlights is of course the spectral resolution and the accuracy, as well as the power level accuracy and the optical rejection ratio, that is 40 decibels for the Redstone as compared to the OSA 2X 30 decibel. The Redstone also has a lower polarization dependence due to the angles inside the instrument. Here you can see the front panel of the Redstone. You can see the 2 input ports, the free space input port, which has a wedged window which can be removed if it gives unwanted optical effects. We have the fiber input port standard with the FC-PC connector. Other connectors are available on request. And lastly, we have the calibration output, where you can connect the fiber from the calibration output to the fiber input port for calibration. The back panel of the Redstone includes the high-speed USB 3 connector to which you connect the laptop. You also have 2 BNC connectors for triggering and recognizing when the device is acquiring data. And you have 2 purge connectors which you can use to purge the instrument. There is also an adapter to the free space input port, so you can purge the optical path all the way to the light source. The Redstone, as well as the OSA 20X, has an alignment beam that can be activated to exit from the free space input port. In the Redstone case, it's activated by the software, and for the OSA 20X, it has an external switch. This is used to align your optical setup for optimal performance with the optical spectrum analyzers. Right, let's do some measurements. I have now hooked up an LLD 1530, a locked laser diode, to the OSA 202. Now the locked laser diode, that's actually the reference laser that's internally in the Redstone. But now it's connected to the OSA 202, and we can take a look. I'm putting a rolling average of 5, but I'm gonna put the resolution to high, apodization to Han, and zero fill factor of 2. We see this nice narrowband peak. We can put a peak track analysis on that. It automatically detects the peak and gives us some details. We can also go to the interferogram view. And here we see a very nice interferogram, sinusoidal all the way. From the wavelength meter, it picks out the period of this interferogram. Let's see how the Redstone fares in real measurements. I've now connected the locked laser diode LLD to the Redstone, to the fiber port, and let's start measuring. I put the Redstone to high resolution using a Han apodization and a zero fill factor of 2 in order to get the highest possible resolution of the spectrum. And as we can see, the spectrum is a narrowband source centered around 1532 nanometers. We can bring up the spectrum from the 202 that we recorded earlier to compare. And we can see that, yes, there is indeed a better resolution with the Redstone. And also the sensitivity is about 5 to 10 dB better. Now I've hooked up the compact broadband source SLS203 to the free space input port on the Redstone. Let's see how that spectrum looks like. I put it on a rolling average of 5. And I haven't purged the redstone. So whatever we're gonna see now, it's a broadband spectrum with some absorption features from the air we have here in the lab. We can see basically 3 different regions with absorption features. One here at 1.8 micron, one at 2.7, and one over 4.3 microns. We can zoom in and check out those absorption features. They're nice and narrow. We can also compare them to theoretical data. So let's open up the references window. Here you can import data from the Hydron reference database, and I've prepared one for water. I'm going to load that as a trace, move it over to the secondary y-axis because they have different units, and then we can zoom in again. I'm zooming with a mouse, zooming with a scroll wheel, and I'm right-clicking to autoscale. And as we can see, we do get a good fit from theoretical and practical data. Let's check this other region at 2.7. Once again, it seems we have measured the water vapor here in the lab. But what about this region here at 4.2? That's not water, and many of you probably know what it is already. Let's see if it could possibly be carbon dioxide. I'm going to load that as another trace, move that over to the secondary y-axis. It does look promising, doesn't it? I'm zooming in and auto-scaling, and yes, it is carbon dioxide. We can do some analysis on these absorption features. We open up the analysis menu, we click on Valley Track. It'll automatically detect the valleys or the absorption features, and it'll give you a table full of data such as centroid wavelength, depth, and half width. I did notice that there was something else from the carbon dioxide. We have some more carbon dioxide absorption features here closer to 2.7. You can zoom in on those. You can see we have multiple peaks here in the measured data. And if I change the y-axis, we see that some of them are closely related to the water and some are from the carbon dioxide. Now I've hooked up a semiluminescent diode to the redstone. It's an SLD1005S. It's in a butterfly mount located in this controller right over here. The SLD is an excellent broadband source with a lot of power, and it covers some tens of nanometers. And this one in particular is centered at 1560 nanometers. So let's take a look at the spectrum. For this, we only need medium-low resolution. And the spectrum is very nice. It's a near-Gaussian shape, centered at about 1560 nanometers as expected. For this source, we can take a look at the interferogram. So let's go into the interferogram view. And here we can see the center burst location of this source. It has a nice bell-shaped envelope and a sinusoidal pattern inside. And for some of these sources, it's interesting to look at the coherence length. Now, this is easily calculated with our software. You open up the analysis menu and you click the coherence button, and this window appears with the coherence length calculated. So for the final part in this webinar, I'd like to show you how to wavelength calibrate the redstone. Now, I don't expect you to do this very often because the calibration is very stable, but it's good to know that you can check the calibration instead of shipping the device over to a Thorlabs location every year. It's what we in Sweden call wearing both suspenders and a belt. So the calibration is very simple. First you connect the fiber, which is included with the instrument, from the calibration output to the fiber input port. Then you open up the calibration assistant, which tells you the process steps. They are quite simple, and the first one I already did by connecting the fiber. Then I press next, and the software will first make a rough measurement to make sure that I have indeed connected the fiber correctly. And then it will start making some more accurate measurements. The results are presented, and in this case we're off by only 0.3 picometers, which is well within the specifications. Thank you so much for tagging along in this webinar. If you have any questions, I'm going to be around for some time to answer them. Otherwise, just contact the Thorlabs tech support and they will guide you. Thanks again for the attention.